Hello, Physics 30s. It's me, Mr. Jukley here again. Going to talk to you. We're still in the EMR unit, still Unit 4. Going to talk to you today about the speed of light. That's Lesson 2, and also Lesson 3, reflection in plane mirrors. Now, Lesson 3, I know that's a lot for one particular video, but they're both fairly short lessons. Plane reflection, actually, if you've got a good sense of trig, is probably the shortest lesson, possibly all in of Physics 30. So we'll get them both out of the way right now. If you need to take a break in the middle, put it on pause, maybe take a note of the timing, and you can definitely split those up. But we are doing Lesson 2 and Lesson 3 in this video. So let's jump right in and let's check out the speed of light. There we go. So one thing that you probably know about light is it's really fast. Really, really, really fast. And you probably already know the number, or at least have heard how fast it is. 300 million meters per second. That's very, 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 very fast. So fast indeed, or in fact, that people for the longest time thought it traveled with infinite speed. And you can think about why that would make sense to a person, right? Without really measuring it very quickly. You flick a light switch on in your house, it is instantly filling the entire room, right? So yeah, I mean, and we've got two big challenges when we're trying to figure out the speed of light. One, it travels really, really fast, so you probably need really large distances. And then two, you need to be able to measure the times very, very, very accurately. So small periods of time measured very precisely. And even the other day we talked about speed of light, and we did an example where a light beam traveled, I think it was something like 75 kilometers in approximately 2/10,000ths of a second, so 75 kilometers. That's crazy. In 10,000ths of a second, just so fast. So how do you measure something? Well, how do you first get something that big, a distance that big, and then second, how do you measure that precisely for the time? So we'll look at some of the ideas that people had through history. One of the first people who thought about this, and we have recorded evidence of this, is Galileo in approximately the 1600s. So Galileo used lanterns and water clocks to find the speed of light between two hills. So even thinking about that, like water clocks, not the best timers that we've got there. So essentially what happened with this is that Galileo and his assistant, and you'll notice in this diagram they look like they're twins, but Galileo and the assistant, they sat on top of hills that were very, 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 very far apart. Galileo would unshutter his lantern, so send a beam of light or a pulse of light is what he's looking at, across the huge valley over to his assistant. As soon as his assistant sees that beam of light or that pulse of light, he quickly uncovers his lantern and sends a pulse of light back towards Galileo, and all the while they are timing this. Galileo in particular is timing this. Pretty cool experiment. The problem is we're not fast enough for this. So humans aren't really fast enough for this. Realistically, you are trying to figure out, okay, let's go to that one. There we go. You're like measuring reaction times is sort of the big idea here. So you're not actually going through and measuring the speed of light in any kind of accurate way. You're measuring how quickly you can cover and uncover a lantern and start and stop your stopwatch realistically. The good thing that Galileo got out of this, well, he was never really close at all to getting the speed of light from this experiment. He knew that it was very, very, very fast, and he knew that it was not infinite. Right? So starting that thinking off is very, very, very important. So knew that it was very fast and knew that it was not infinite. And then let's just go back to this one for a second. This is something that we learned about in reflection in Physics 20. So if I go at the one-way distance, starting here and going over to here, which I might show as capital D, and I know that light travels with uniform speed, I'm going to use V is equal to D over T, the distance divided by the time, but the total time that Galileo was using his water clock over here is the time that it takes to go all the way there and all the way back. So that is 2 times the one-way distance. So again, just something that we looked at last year and something that we need to be familiar with again this year. Cool. So very, very fast. Next people we want to talk about are Romer and Huygens, about the 1700s again. You can tell because of their hairdos. But essentially what they did, people started to have a really good idea of like orbits and know that like moons orbit Jupiter and Jupiter's orbiting the sun, and we're also orbiting the sun at this point in time. So what they started to look at with this, and you remember a lot of this from circular motion probably, well, hopefully, from Physics 20. But what they started to do is they used the eclipse of Jupiter. So there's one of the moons of Jupiter, and there's its eclipse on the surface of Jupiter. And they use that eclipse that should be showing up at regular intervals to help figure out the speed of light. Now notice I said should be showing up at regular intervals because that moon around Jupiter, well, it orbits Jupiter at regular intervals. Cool. So yeah, we know that the moon orbits Jupiter at regular intervals, and they knew how long those regular intervals were. So what they noticed was when the Earth is closest to Jupiter, so notice at position A over here, it's closest to Jupiter, the time of the eclipse came earlier than expected. So this alignment over here for the moon of Jupiter came earlier than expected. And then when the Earth was further away, so on the opposite side of the sun to Jupiter, so Earth is now in position B over here, they noticed that that eclipse, so this same orientation for Jupiter and its moon, came later than it should have, or later than expected anyways. The further away you got, the later it came. So essentially what they did was they took the maximum difference between the earliest and the latest, and they said, okay, the earliest should be when we are closest to Jupiter. The latest is when we're furthest away from Jupiter. So they figured out that it took 22 minutes longer when it was at position B than A. So we've got time. And remember, what do we need to calculate speed? We need distance and time. So they calculated the time, or figured out the time, I shouldn't necessarily say calculated. And then they knew at this point in history, they knew the Earth's orbital radius. So if we know the radius, orbital radius, we should be able to get the diameter. So if I've got the diameter, this distance across, and I've got the amount of extra time that it takes that light to travel, well, we've got distance, we've got time, we should be able to figure out the speed of light. So they went ahead, they did the math on this, they figured out the speed of light being 2.3 times 10 to the power of 8 meters per second. Now that's not perfect, right? Our known value right now is 3.00 times 10 to the power of 8, but at least it's in the right order of magnitude, and we're getting very, very, very close. So pretty cool experiment there. Now the one that we need to spend a bit more time on is Michelson's rotating mirror experiment in about 1880. So the idea with this is, and we'll just sort of start walking through it. He's got an 8-sided mirror, so the mirrors, maybe I don't know which one's better. The mirrors are all along this side of our 8-sided octagon. So I'm shading them in here so that light, when it comes in, it bounces off in this direction. Let's clean this up a little bit because I'm making a huge mess here. You know what, let's just get the eraser and go like that. Cool. So when the mirror is not rotating, essentially what we have is we have a light source. I'm going to draw it as a light bulb to show our light source. And the light ray, so one ray of the light, maybe I need a different color to kind of highlight this, would come down. It would reflect off the mirrored surface. It would go over to a secondary fixed mirror. So our fixed mirror is over here. It would reflect off the fixed mirror. And as long as this, this 8-sided mirror is in the correct orientation, it would come down, and then a person could detect that. So it says an eye, that would be a person or somebody looking to try to detect that light. So as long as it's in this orientation, the light bounces off the 8-sided mirror, bounces off the fixed mirror, comes back, and the eye can actually see it. If it's rotating, but it's rotating and the light is bouncing off, so we had that light pulse that's coming in, that light pulse comes over here, bounces off that mirror, that light pulse comes back. And when it gets back, if it's in the wrong orientation, so my mirror has been rotated, but it hasn't rotated back to the correct orientation, the eye would never see that, right? Because the light would come off, it would bounce off here, the person over here would be very sad because they would never be able to see the light. Actually, they probably wouldn't be sad because that's a very important part of the experiment. Cool, so it needs to be back to the original orientation. So what we want to look at for this then is understanding the minimum frequency and how important that minimum frequency is. Can I still move that? Ah, perfect. How important that minimum frequency so that the person could see the light. So that light ray is bouncing off the eight-sided mirror, and if it's got the right frequency, the eye will still be able to see it. Perfect. So let's see here. Deriving the formula is the next big thing that we want to look at. So I'm deriving the formula. We know that light travels with uniform motion. So we know V is equal to D over T is our formula. Our distance, like the total distance for this light beam, if it's got to go from here, and we're looking at the diagram on the right-hand side, over to the fixed mirror there, and then back, the distance, the one-way distance we can call capital D. So then the total distance would be 2 times the one-way distance, 2 times capital D. Perfect. Now the time's a little bit trickier. Time is a little bit trickier. So if we're looking for the minimum frequency, that would be our maximum period. And we're starting to relate that period to frequency, right? So as I go back, I'm kind of thinking about the minimum frequency to be able to see this. And this is why I have this so I can rotate it. Does it really need to rotate? So notice the orientation now where I've got line segment AB on the top. Does it really need to rotate all the way back around so that I've got AB on the top again to get back to the same orientation so that the eye would see it? Or does it just need to rotate to here? Yeah, it just needs to rotate to there. And then it's essentially, I mean, line segment AB is now shifted, but it's realistically the same orientation so the eye would still see it. So how much of a full rotation is that? If you're thinking that it is 1/8 of a rotation and then 1/8 of the period, you were spot on. So our new formula that we're looking for, or that we're looking at here, V for the speed of light for these Michelson experiments or Michelson experiments is 2 times the one-way distance divided by 1, and I'm going to make this very general, 1 over n times the period. So then just the reason why I put it 1 over n is we're using 8-sided mirrors, but it doesn't necessarily need to be an 8-sided mirror. It could be a 10-sided mirror, 12-sided mirror, 16-sided mirror. So n is just the number of sides that the mirror has. Perfect. So take a moment to check this out. You can put it on pause if you need to, but we're going to move forward and we're going to check out a quick example of this. Oh, but even before that, Michelson was the first person, the first North American to win the Nobel Prize for this. Very cool. He was actually quite close to 3 times 10 to the power of 8 meters per second, our currently accepted value of the speed of light. I should also mention, before we get into examples here, I got ahead of myself a little bit there, that realistically today we can use lasers and more accurate timing to figure out a more precise value for the speed of light, 2.997924.562 plus or minus 0.000000011 times 10 to the power of 8 meters per second, which we typically round to our standard 300 million meters per second, or 3 times 10 to the power of 8 meters per second. Cool. Okay, a bit of review stuff here. If a mirror rotates at 800 RPMs, what is its period of rotation? So remember 800 RPMs, that's rotations per minute. So I would write that out as 800 rotations per minute. Now, if I wanted the period is my total time divided by the number of cycles. So my total time is 60 seconds over 800 cycles. Oops, almost put seconds on the bottom. Cycles. And when you divide that out, I have no idea what the answer is for this. Quite frankly, I don't really care too much as long as we understand how to do it. So we divide that out, it would be the seconds per cycle. And that's our definition of period. Cool, so make sure we know how to deal with that one. So here's our actual example. I got ahead of myself, but here we are. So we got a Michelson 8-sided mirror experiment. The mirror rotates at a minimum frequency of 36,000 RPM. Cool, that's how we see the light. The measured speed of light in this experiment was 2.7 times 10 to the power of 8 meters per second. determine the distance between the mirrors. So that's from one mirror over to the other mirror, not the total all the way there and back, but just from one mirror to the other mirror. So first thing that I'm going to do, that 36 RPMs, I'm not really going to deal with that. I'm going to deal with period, because I know that that goes in the formula. So the period is the total number of, the total time divided by the number of cycles. So that's 60 seconds over 3,600 cycles or rotations. So 60 divided by 3,600 should be 1.666, and I believe it's a repeating number, 7 second. Oops, I forgot something very important there. Times 10 to the power of, let's see, negative 3 seconds. There we go. That would have been a pretty big mistake there, forgetting 10 to the negative 3. But we figured it out. Cool. So now we can start to look at our new formula. We say V is equal to 2 times the one-way distance divided by 1/8 times the period. I'm using 8 because it is an 8-sided mirror. It tells me right in the question, times the period. Cool. So I am looking for the one-way distance. So I just need to rearrange and solve for the one-way distance. So one-way distance is going to be equal to, let's see, V times 1/8 times the period, all divided by, let's see, all divided by 2. Cool. Now that fraction inside of a fraction can be a little bit annoying. So you can turn that into a decimal if you want to. You could all recognize that multiplying by 1/8 is the same thing as dividing by 8. You could also just plug it in as is, and you'd probably still get, no, you would definitely still get the same thing. So let's go ahead, let's plug some numbers in. D is equal to V. So I think it was, yep, there it is, 2.7 times 10 to the power of 8 meters per second times 1/8 of the period. So I'm going to multiply that by 1 and divide by 8. I could even, if I have my calculators open, I could show you how I'd plug that in, times the period. So that's 1.6666. We're just going to keep a whole bunch of those in. 7 times 10 to the negative 3 seconds, and then we're going to divide this whole thing by 2. So let me just show you exactly how I would plug that in, just to be clear, as soon as the old calculator turns on. Oh, and I forgot to divide by 2. Forgot to actually put the number in there. So I would do 2.7 times 10 to the power of 8 times 1 divided by 8. So there's my fraction right in it, times 1.666666, whole bunch of them, 7, 10 to the negative 3. Just double check I got it in there right. And then divide by 2, and we end up with, holy moly, 28,125 meters. We don't really want this in with that many sig digs, so we could either do 2.8 times 10 to the power of, let's see, 1, 2, 3, 4. So 2.8 times 10 to the power of 4 meters, or we could go through and say 28 kilometers. Again, that's the distance, that's the one-way distance between the first mirror, the rotating mirror, and the fixed mirror. Cool. Pretty fast. So in 1.6 times 10 to the negative 3 seconds, it goes 28 kilometers. Pretty crazy. Pretty crazy. Cool. So the next little bit here is just kind of talking about, and we'll see when we get into this unit as well as Unit 5, our atomic physics unit, different ideas and different evidence that says that light is a particle, and some evidence says that light is a wave. Today, you might be a little bit disappointed. We are talking about, and this is, by the way, now into Lesson 3. So you might want to either take a little breather depending on how you're doing, focus on Lesson 2 practice for a little while, or if you're feeling confident, you're feeling good, you can just stick with me and keep powering through this one. But this is Lesson 3, and yeah, let's check it out. So reflection in plane mirrors. So by plane mirrors, we mean totally 100% flat, and that I realize is not totally 100% flat. Let me do a nicer one. There we go, totally 100% flat mirrors. So yeah, and I mean, light does reflect, which, okay, let's go back there, and follows the law of reflection, which I mean is evidence that, well, waves does do that too, but so do particles, so not very useful in that argument. So our law of reflection, you actually talked about this in physics 20. We said that our incident angle is equal to our reflected angle and always has to be measured compared to the normal line. Normal line is just a line that is 90 degrees to the surface. So normal line is always 90 degrees to the surface. Normal is the new 90 is what they say. So anyways, always measure compared to that. So my incident angle, let me clean that up a tiny bit. My incident angle compared to the normal, my reflected angle, again, compared to the normal, not compared to the surface. But that being said, would the angles compared to the surface be the same as well? So like I'm just gonna label these in some other colors here, maybe black. Let's call this theta x and theta y. Would those two angles be the same? Absolutely, but that is not how we want to label our incident and reflected angle. That'll mess us up when we get to the mathy bits later as well. The other thing that I want to note with this is that we are being very specific that this is a lowercase r. Capital R is when we talk about refraction. So theta capital R, these two things are not the same. Do not use this for reflection. That one is for refraction only. So be very specific. Reflection is lowercase r with respect to the normal line again. So again, kind of useless when we're looking at whether light is a wave or a particle, because both waves and particles reflect and follow this law. Anyways, what we've got here, first and only kind of mathy thing, I suppose, for this is can we figure out how this light ray is going to bounce off of mirror B? So we get a light ray coming in. It's hitting mirror A. It's obviously going to reflect off of mirror A. And let's even trace it out a little bit here. So hits mirror A, reflects off of mirror A, hits mirror B, and then reflects off of mirror B. I think I got to draw. Oh no. Okay, hold on. There, that might be a little bit nicer right there, actually. Okay, and then so hits mirror B, and then where was I there? Hits mirror B and reflects off of mirror B, something like this. And we're looking for our angle of reflection. So get back to my felt pen here. Angle of reflection off of mirror B. So I got to figure that one out. So I can draw a normal line here, and this angle is 21 degrees. So I could figure out that my incident angle, and I'm going to label that with an N for normal line, my incident angle off of mirror A is, let's see, 90 minus 21. Well, that's 69 degrees. But do I really care that this angle right here, I'm going to draw it in red because I don't really care. My incident angle, my original incident angle is 69 degrees. Does that really matter too much to me? Not particularly, because if that angle is 69 degrees, my reflected angle is 69 degrees, and then this angle is also 21 degrees. Perfect. Okay, so technically not my incident or my reflected, but still 21 and still useful. Okay, next little piece that I want to look at here is, okay, so I have to figure out maybe this angle, and if I could figure this angle that I've got in, let's do red, if I could figure out that angle down there, then I could figure out this red angle over here as well, which again, not the most helpful, but could lead me to my normal line. Cool, or sorry, not my normal line, my reflected angle. Only problem is, I have one angle inside of a triangle, but that's about it right now. So this line right here, okay, let's see. This line right here, that's a totally flat line, so this angle plus this one should make 180 degrees, because a flat line is 180 degrees. So if I wanted to figure out what that black angle inside of the triangle is, I do 180 minus 76, and turns out to be, better get a bit of a skinnier felt pen here. Let's just make it like that. This angle turns out to be 104 degrees. Nice. So that black one inside of the triangle, 104 degrees. Now the red one, when I switch and I'm looking at this red one in here, that angle. Maybe I'll label it from the bottom. Might be a little bit nicer for later on. Shoot, too many colors going on here. Sorry, folks, bear with me. That red one right there is the next thing that I want to figure out. So I've got a triangle here. I know the triangles have to add up, the angles inside of triangles have to add up to 180 degrees. So I've got 21 and 104, and I'm looking for the third missing angle. So I'm going to do 180 minus 21 minus 104, and that's going to give me 55 degrees. Perfect. So now I know that red angle is 55 degrees. We'll use one more color here. This is very colorful. I'm going to first put my normal line, and actually I'll draw a nice neat straight line for that. Let's do like that. I'm going to put my normal line, not an arrow technically, but my normal line going straight up there, 90 degrees to the surface. So if this is 55 degrees, the angle that's left over that I'm going to put in blue, which is technically my incident angle off of mirror B, well, should be 90 minus 55. So let's plug it in. 90 minus 55. Oh, that's 35 degrees. Clean up a bit of space here. Get a skinnier felt pen because that's not helpful for me. So theta I is equal to 55 degrees, which means our reflected angle, our very last angle, theta R, must also be 55 degrees. So that is our final answer for this one. Now there's a little bit to get there, but realistically, it's some pretty basic trig, right? Our angle, our law of reflection is our incident must be the same as our reflected. And then after that, you know, flat lines add up to 180, angles inside of triangles add up to 180, and right angles have to add up to 90. It's pretty much all we did there. So not too bad. Okay, next piece to look at is images in plane mirrors. This is like looking at yourself in a mirror. And why do we see the image the way that we see it is what we want to look at. So things to think about. We want to think about a point source of light. So the point source of light, back to this one, is just this thing that I'm currently highlighting. It used to be yellow, now it's, I don't even know what color you'd call that. But that's giving off light. Light is coming off of that point in all different directions, and it's radiating outwards in all different directions. When we see that light, essentially our eye receives a cone of light coming from the point source, and where the cone comes together, so right here, is where we perceive that object to be. So where those rays come together, that's where we perceive that object to be. Perfect. We see that image. Nice. So if I'm just thinking about seeing that object now in a plane mirror, remembering that it's light rays going out in all different directions, essentially what we have, if I focus on just a couple of those light rays and we trace them out, they're coming, they're hitting the mirror, they're following the law of reflection, and they're coming off of the mirror. Perfect. Same thing with the bottom one, following, coming out of the object, reflecting off the mirror, and then coming in and meeting our eyes. Now when we think about where our eye, because our eye and our brain understands that light, for the most part, travels in straight lines. We perceive light traveling in straight lines. So where does it look like, and let me just erase this and clean this up a little bit, where does it look like these two rays are going to come together to us? And if you guess, behind the mirror over there, absolutely, right? Because the brain thinks that light travels in straight lines. So wherever those two things converge is wherever those two rays converge is where the object is going to be. So it thinks that they're converging back over here, traveling in straight lines. So we see the object behind the mirror. So one thing that we'll get used to as we go through, there's no real rays coming from behind the mirror. So it's actually a virtual image. And anytime we use virtual images, we use dotted lines to help represent that they are virtual. So that's something we want to keep in mind as we go through the course. So things to note for plane mirrors, there's loads and loads and loads of symmetry. So the distance to the mirror, the actual object to the mirror is the same as the distance to the image to the mirror. And you know, we can look at things that are a little tiny bit trickier. So this person is standing in front of the mirror. If we want to understand what this person sees, we can think about a point source of light coming from the top of her head. So giving her I don't know, something on the top of her head. Um, it comes in, it reflects, and it comes off. Where does it look like she's seeing that? Well, it looks like she's seeing that coming from all the way up here. So we see that image, perfect, and it looks like she's the opposite distance. If she wanted to look at her feet, so you've got a little ray of light coming off of her feet, it's reflecting off the mirror, it's coming back to her eyes, but where does it look like this ray of light in her perspective is coming from? It looks like it's coming from way back here, again, behind the mirror. So cool, not too bad. Now we will need to, as we go through the course, start describing things very specifically with images and mirrors. So we want to look at the magnification. Plain mirrors, it's really easy. It's the same size, right? You look at yourself in the mirror, you're the same size. You're vertically upright, but you're wrong part, vertically upright, but laterally inverted. So what that means is you might have your right hand for the image. It would be the left hand of, sorry, your right hand for you, it would be the left hand of the image. So laterally inverted, inverted just means flipped. It is virtual, so they are not real light rays that are coming out from behind the mirror. And then how far from the mirror? Well, the image is located the same distance behind the mirror as you are in front of the mirror. So cool, we'll get used to all those things as we go through and look at other things. So one activity that we've got is, could we sketch what this object looks like in our mirror? So things that I want to do with this is I'm just going to pick a couple key points. So I'm going to pick this point, and then obviously the arrowhead as our last point. So I want them to be equidistant from the mirror. So all I'm doing is I'm measuring with my fingers right now, to be totally honest with you. So there's the arrowhead. This other one, okay, so let's go to about there. So that's the second dot, and then the bottom dot is about there. Somewhere in that sort of range. Now this might not be perfect, there's a better diagram later on. So I've picked 3 major spots, and now all I really want to do is connect those dots. So here, and then back up to there, and we get a somewhat crummy image of that object. Here's a much nicer one though. Here's a much, much nicer one. So again, equal distance, but reflected back is sort of the key. Cool. So one application is cheating in billiards, or at least learning how to use billiards. So you can actually set a mirror up to see where you want your cue ball, that's the white one, if you're not familiar with billiards, where you want that to go, because it will follow the law of reflection. Okay, last little bit to talk about here is just different parts of that electromagnetic spectrum. So, you know, raging Martians invade Venus using X-ray guns. So our order of this. Radio waves is one thing that we really want to talk about today, and that's kind of our focus for today. So we got two main different types of radio waves that we look at. We've got AM radio waves, that stands for amplitude modulation. They typically carry lower frequencies, so in the kilohertz range, that's thousands of hertz. They have way better receptions at a distance, so they can go thousands of kilometers. And if you're driving around in your car through Alberta, you would know that. So you're listening to CBC on FM, you lose it real quick. On AM, you get that CBC radio 2, or sorry, radio 1 just about anywhere. One of the reasons for this is because it reflects off the ionosphere. So it actually reflects off of our atmosphere. One of the reasons. And does a better job. FM radio stands for frequency modulation, and it's typically on the scale of megahertz. It does not reflect off the ionosphere and has way poor reception at a distance, like hundreds of kilometers. So different things that we look at. Typically, the shorter the wavelength, and we better go back to that, V is equal to frequency times wavelength. So they all travel at the speed of light. So that means really we only look at frequency and wavelength, and we know that those have an inverse relationship. So shorter wavelength or higher frequency typically has better penetrating abilities. So they can go through walls and stuff like that. So FM radio can go, you know, straight through the wall of your house. You can use it for cell phones, all cordless phones, all kinds of different things like that. AM, less so. AM radio waves, another thing, it's a much longer wavelength. Remember, so a lower frequency So smaller frequency means a longer or bigger wavelength. So in order to pick up some of these long radio waves, the really long radio waves, you need huge satellites in order to be able to see them. See as in quotation marks, because you don't really see them like you would visible light, although they're very similar to visible light. So again, you can have one huge satellite, or you can have a bunch of smaller satellites acting as one huge satellite. So there's a little bit about radio waves, both AM and FM. It's pretty interesting stuff, actually, if you want to check it out a little bit more, but I think that's going to conclude our lesson for now. It's been great talking to you, Physics 30s, and yeah, we'll see you again soon. Bye for now.